Hello everybody, welcome back to Networks class. So last time we went over the details of homework 0, and the plan for today is to go over the details of this GAMS prep homework, where we'll both look at our first model of a real world situation using shortest paths, and we'll go off and try to solve the actual problem in GAMS. So I'll show you a little bit about how to work with GAMS today. So first, let's talk about trying to model this problem. So you should all be familiar with this because you spent some time thinking about it. So it was a single duty crew scheduling problem. We have these duty hours here, and what we have to do is figure out the minimum cost to cover everything from 9 to 5, and each of these columns here represents a person we can hire. So this person can work from 9 to 1, and if we have him come in at all, we have to pay him 30. So there's a number of networks that you could create to try to solve this problem. But the important part for creating these networks is that you have to define your nodes. You also have to define the edges, and then you also have to define start node and end node, and you have to define some edge costs. So this first part, to define your nodes and edges, this defines the graph. And the second part, giving a start node and an end node and some edge costs, this defines a shortest path problem. So let's think about how we can create a graph for solving that single duty crew scheduling problem. So there's actually many different ways to do this. So let me just explain a few of these. So the first way of doing this is to create one node for each of these duty hours. So for example, here we have a node from 9 to 1. The next duty hour was 9 to 11, so we have a node for that. So 9 to 11. Another one from 12 to 3. One from 12 to 5. And so forth. Maybe another one from 4 to 5. So I won't write them all out, but you get the idea. So we create one node for each duty hour. So so in terms of writing this down, we have to do these things that we said earlier. So let's write down what nodes we created. So we create one node for each available person. Or you can think of this for each available duty is what the problem calls it. But so we created one of these nodes, and then we're going to create an S node and a T node. So here they are, S and T. So now we've created the nodes for the graph. But the next thing we have to do is we have to define some edges. So create edges from S to every shift starting at 9. So that would be S to 9 right here and S to 9 right there. The next thing we need is to create some edges from every shift ending at 5 to T. So that means this 12 to 5 shift is going to get an edge to t, and this 4 to 5 shift is going to get an edge to t. So we've now connected S and T to the graph, but we have to create the shifts together. So create an edge from shift AB to shift CD. So in other words, this might be a 9 to 1, and this one might be a 9 to 11. If there's basically an overlap in the shifts. So in other words, C has to come in somewhere between A and B, and then D has to be somewhere bigger than B. So we're going to connect the earlier shift to the later shift using this rule. So using this rule, we're going to have an edge here from 9 to 11, and what 911 to this 9 to 1. And what this edge represents is that after the person that covers 9 to 11 gets completed, the next few hours might get completed by this person who can work 9 to 1. So, but there's not going to be an edge from 9 to 11 from 12 to 3 because that kind of leads a gap in the hours here. So some other edges that we'll have here is 9 to 1 is going to have an edge for 12 to 3. 9 to 1 is going to have an edge from 12 to 5. And 12 to 3 is going to have an edge to 12 to 5, etc. And we're not going to write all of these down, but that's the basic idea. So besides creating the edges, to define the shortest path, we have to give edge costs. So we can put the cost of a shift on edges exiting the shift. So for example, this 9 to 11 shift, it cost $18, so put a cost of 18 right there. The 9 to 1 shift cost 30, so we'll put costs of 30 here and here. The 4 to 5 shift cost 9, so this will be a cost of 9. And the 12 to 5 shift cost 38, so this will be a cost of 38 right there. So now pretty much all the edges have costs except these edges out of S. So the edges out of S, we're going to say have 0 cost. So 0 for this guy and a 0 for that guy. And so now we've totally defined the graph. S is going to be our start node and T is going to be our end node. And now a shortest path from S to T is going to tell us who to hire. So how do you know that the graph that we've constructed here actually gives you a minimum cost schedule? So these are the things that you can try. So in terms of debugging your model, the thing that you need to do is kind of think about creating alternate data. And if your method for constructing the graph, works every time. So it might be the case that somehow you looked at this data for this problem and you created some graph that's very specific to the data that you just happen to be seeing right now. But that's not what we're looking for. We want some kind of model that works regardless of what data happens to be in here. So somebody could come along and give us totally different duty hours, and our rules for creating the graph should work just as well. So we're going to use that in a little bit to debug some ideas. But you can also just directly prove that your graph is going to give you a minimum cost schedule. So if the following two things are true, so if every schedule corresponds to a path, and I really mean every feasible schedule, if every feasible schedule corresponds to a path in the graph of the same cost, and if every path in the graph corresponds, and really it's every path in the graph from S to T. So if every path in the graph from S to T corresponds to a feasible schedule of the same cost. So if these two things are true, we basically have a one-to-one correspondence between feasible schedules and paths from S to T. And so if we have this one-to-one correspondence, finding the shortest path from S to T is going to give us the minimum cost schedule in the graph. And so if you wanted to prove that your graph works correctly, these are the things that you would look for. We're not going to really do that in class, but it's something that you can think about in terms of trying to debug your models. So let's think about a few other ways of modeling this problem besides this particular graph. So the first thing to point out is that the costs here right now, I have them on the edges that are exiting the shift. But I can put them on the edges entering the shift just as well. So the following graph would work just as well, which is instead of having the costs where they are now, we're just going to move them. So now this 9 to 11 shift, instead of paying on the $18 for it on the way out, we can pay the $18 on the way in. And so we'll pay the $30 on the way into the 9 to 1 shift. This edge here is going to have the cost of the 12 to 3 shift, which is 21, and so forth. And now on this other end, we're going to have the zeros when we go to T. So this works just as well because we're accounting for all the costs just as well. So that's another way of solving the problem, but there's actually several other ways. So let's look at a few other ways. So here's a common one that people come up with. So to make each hour be a different node, so 9, 10, 11, 12, 1, 2, 3, 4, and 5. And so just to keep track of what we're doing, so what we did was create one node for each hour. And now typically people then say, well, let's just add some edges to the shift. So the 9 to 1 shift can cover 9 to 1 at a cost of 30. So that means we can go back here and put this arrow from 9 to 1 at a cost of 30. And so you can go back and sort of do the rest of these. For example, 12 to 3 at a cost of 21. So 12 to 3 at a cost of 21, and so forth. But so just putting in these edges directly is not enough. So here's an example. So suppose that I just had 5 hours here, and I had one person who could cover sort of the first 4, and another person that could cover the last 4. So if I just put in these two edges And then this is my start node, and that's my end node. If I look for a shortest path from S to T, at this point, there is no path from S to T. And so the problem is going to come out as infeasible. So we don't have this one-to-one correspondence between feasible coverage and paths. So you have to do something extra. And there's a number of ways you could fix this. So one way that you could fix this is by just adding these backwards edges of cost 0. And if you add these backwards edges of cost 0, you're basically saying you have to pay some amount, maybe $10, to get from S to here. And then you can backtrack at 0 cost, and then you have to pay again if you want to move forward and cover some extra time. So that's one way to fix it. So that would be create a edge from A to B at cost C for a duty hour AB that has cost C. So that would be something like this 9 to 1 at a cost of 30. And then create 0 cost edges from each hour j to the previous j minus 1. So that would be things like this: 0 cost, 0 cost, 0 cost. And then, of course, so now we've defined the nodes, we've defined the edges and their costs, and we have to define a start and end node. So the start node is going to be node 9, and the end node is going to be node 5. And so now we again have this one-to-one correspondence between paths and feasible schedules, so this works just as well for solving the problem. But let's see another way of solving this issue. So if I had the same problem, the problem is that if you just add the edges for the duty hours themselves, then they're not connected. And so one way of fixing this is to just add some more edges for each duty hour. So here I would add these edges of 10, and then I would add these edges of 15. And so what this is saying is that I could use this person to cover 9 to 1, but I also could use them to cover 9 to noon or 9 to 10 or something like that. So I can use them to cover kind of subsets of things. So if you do this, this works just as well. And another thing you could do is the following, which is when I have one person like this and one person like this. So here, and our first approach is to solving this. We kind of moved the front end of the edge back, but you could move the back edge forward. So you could just add these edges right here. And of course, we'd be doing that for everybody. So we would be moving this one forward as well. And so both of these solutions work. So one of the things that might happen as you do this is that as we're creating all of these edges, we might have kind of a couple of hours here that get a couple of edges between them. So maybe this first edge came from one duty hour and the second edge came from another one. So this bottom one maybe came at a cost of 10 and the top one at a cost of 20. So if this ever happens, we know for a fact that the shortest path is not going to use the cost of 20 edge. So we can just drop that one from the graph and get back to having a regular graph instead of a multi-graph. So you can just take the minimum one. So so that gives you at least 4 or 5 ways of solving this problem. So here are the 5 ways. 2 over here, depending on which side you put the costs. 1 over here with the backward zeros. and 2 over here depending on which side of the edge you move forward or back. So many different ways of solving this problem. And in GAMS, I believe I implemented this particular one, number 2. Okay, so let's see how to implement some of these models that we came up with in GAMS to actually get the answer. If you go to the class website, right next to the GAMS prep homework, you'll see a link for some solution files. So if you click there and you download those, you're going to get a directory with a whole bunch of files. So over here I've downloaded and unzipped that directory, and it has many files, so you may not remember what they all mean. But there's a README file over here you could take a look at to see what they mean. So let's just open up this README file with WordPad. So the README file kind of spells out what all the different files in the directory are. So the first couple of files are just some solver options. So this is the way that GAMS communicates with the solver to let the solver know what algorithm to use to solve the problem. So we're going to look into these files later in the quarter, so you'll know what's in there. But for right now, you can ignore them. So the next file is this input data, hours cost data. So let's take a look at that. So if you open up this file, you'll see that it's basically exactly what was in the table in the handout. So this is the 9 to 1 duty hour at a cost of 30, the 9 to 11 duty hour at a cost of 18, and I just made up some names here to go along with the people. So maybe Alice can cover 9 to 1 at a cost of 30, and so forth. Now, in reality, if you were to try to implement such a program, so for day-to-day activities, and you had to solve it multiple times, let's say once a day, the way that you would do this is you would take that data from the CSV file, and then you would write a small custom pre-processing program. So this pre-processing program would be written in Java or VBA or Python or whatever language you're comfortable in. But what this program does is it creates the graph out of your model. So it exactly creates these graphs that we were talking about earlier. And it's going to spit out those graphs in a CSV file that then GAMS consumes to take out the answer to solve for the shortest path. And if you need to, at the end, you might sort of post-process the answer to create a pretty report or a picture or something like that. So in class, we're not going to do all of these steps. We're just going to focus on these middle steps. So we're just going to concentrate on GAMS taking in a CSV and outputting an answer. And so for the purposes of class, you can just kind of hard code the network here that GAMS is going to read. But knowing this big picture is kind of useful so that you can know what's the rest of the stuff inside of the directory. So if we go back and look at the README file, the next thing that you'll see is that there's a pre-processing program. So this pre-processing program is just something written in Python that takes in that input data and outputs the network. So this is the network described in comma-separated value files for GAMS. So let's take a look at some of those files. So one of those files is a node set. So here you can see that we have a node for each hour. So a node for hour 9, 10, 11, 12, 1, 2, and so forth. And we also have an arc set that describes the various arcs in our model. So for example, let's see. So here we have arc from 9 to 1. And here we have a arc from, let's see, there's one from 10 to 1 right there, from 10 to 1. And there's one from 11 to 1 over here. And there should be one from 12 to 1 somewhere. Yeah, that's where I am. So 12 to 1 is right there. So basically, in terms of implementing one of our models, the models that this particular program is implementing is this one, where for the 9 to 1 duty hour, we also created a 10 to 1 and a 11 to 1 and so forth. So it's just the second one that we're implementing in GAMS. But let's go and look at the actual GAMS file that comes with your download so that we can understand what the various pieces of it are doing. So the first few lines of the GAMS file here are not that important. You can look up what they mean with the various resources that I've emailed you. But the next two are maybe more commonly changed. So these two lines, LP and MIP, tell GAMS what linear programming solver to use. And so here I've specified the Coin CBC linear programming solver. Of course, previously you might have seen Cplex or some other solver written in here. And then the MIP solver is what GAMS is going to use to solve a mixed integer program. So we might change those later in the quarter. So let's continue reading through the program here. And this is reasonably well documented. So if you miss something that I'm saying, you can go back and just read the file and understand what it's saying. So this first line here, what we're doing is we're reading in the node set. So here we're telling GAMS, okay, we're going to define a set and we're going to call it n. The word nodes here is just a comment. So I could substitute this word with any other word and it wouldn't make any difference. And with this $include, what we're saying to GAMS is go off and take a look at this file, the node set file, and in there you'll find all the elements of the set n. So let's go and look at the node file. So in the node file, now GAMS reads all of these things and knows that each of them is an element of the set n, which is going to be our nodes. So in the next line here, what we're saying is that this set n, besides calling it n, we might want to call it something else. So we're saying that we can also use I and j to also mean nodes besides just using n. Following that, we're going to read in the various edges of the graph. So here we're defining a set. We're going to call the set arcs. And the I and the j here basically say that each element of the arc set is defined by a node followed by another node. So the I means that it's going to be one node, and then the j means that it's going to be followed by another node. And down here, we're telling GAMS that the arc set is defined in this arc set CSV. So let's go take a look at this arc set CSV. So that's this part right here. So this is telling me that there's an arc from hour 16 to hour 17, an arc from hour 9 to hour 13, and so forth. So going back to GAMS over here, we've just read in all of the edges. But now what we have to do is define all of the data for each of the edges. So each edge, for example, has a cost associated with it, maybe a person that created that edge. And so we want to read in that data, but when GAMS associates data with things, it basically does not allow you to associate anything other than real valued numbers. So associating the name Alice with an edge is something that's pretty difficult for GAMS. And the only way that we can do it is if we tell GAMS ahead of time what are all the string values that we're going to associate with things. So that's what this acronyms file is doing. So if you go and you look at the GAMS acronyms, here it's all the various names of the people: Alice, Bob, Carl, Dave, etc., George. So now we've defined all of the names that we're going to associate with data, or all of the strings that we're going to have as data. And in the next part here, we're reading in a data table. So this data table is going to be called arcs data. And the I and the j here says that the first two columns of the data table are going to be nodes. So the first column is going to be a node, and the second column is going to be a node. And then the star here says that after those first two columns, we can have an arbitrary number of other columns. So let's go, and down here we're just saying that GAMS should read in this data from the arcs data file. So let's go look at this arcs data file. So here it is. So its first column is a node, its second column is a node, and after that we have an arbitrary number of other columns. So for example, here's a cost column, and we're associating a cost of 9 with this arc, and we're associating a person, George, with this arc. And if we wanted to, we could create some more columns here. So for example, I could have a fuel usage column if I wanted to, and then with each arc I would associate sort of some kind of fuel usage. So now we've read in all of the edge data. So let's continue with the program here. The next thing that we have to do is actually define the linear program for solving shortest paths. So the first thing to do in defining the linear program is we have to define some variables. And so here we're defining a variable z that's going to hold the objective function value. And these y variables that we had in our shortest path linear program. So if you remember, our shortest path linear program looked something like this. So minimize the sum over all edges of Cij times Yij. So the Yij were these variables that we had that said, is a truck going to use this arc or not? And the reason that these variables are positive is because if you recall, we talked about this small piece of magic that we actually want them to be binary, but having them be positive is good enough. So if you solve it with positive variables, you know for a fact they're going to turn out to be binary at the end. So the next part says that we're going to define a couple of equations here. So first we're going to define an objective function, and then we're going to define a network flow equation. So these are going to be the constraints that basically say the number of trucks coming into a node has to equal the number of trucks going out. But the important part here is this parentheses n. So this is saying to GAMS that we're going to define one of these constraints for every node. And the reason it knows that is because n is, of course, the name that we gave to the set of nodes. So let's go through and look at how we define these equations. So first we have the objective equation. So z is then going to be equal to the sum over all edges of now the cost of that edge. So the way that we access that is we look at the arc data table, we look at edge ij, and then look at the cost column. So that's how we access the cost for that edge. And then we multiply that times yij, which is the variable for that particular edge. So this directly corresponds to what we had in our LP here. So it's the sum over edges, the cost times the variable for that edge, and that's what's going on in GAMS. Sum over the edges, the cost times the variable for the edge. So then we have to define the network flow constraints. So here we're doing a sum over all edges. Okay, so these network flow constraints, there's one for each node. So that's what this parentheses j is also saying, is you can think of it as a loop. So we're looping over all of the nodes, creating one constraint for each node. And so inside of here, you can think of j now as being the specific node for which we're defining the constraint. So this first term is basically summing up over all arcs that are going into j, the y variable for those arcs, and subtracting out all of the arcs that are going out of j, the y variable for those arcs. And so this is exactly like what we had in our linear program, just the sum of everything that goes into the node minus the sum of everything that goes out of the node. So the left-hand side of this equality is pretty, we've written that down. But on the right-hand side, we have either a 0 or a -1 or a 1. So let's see how that shows up in GAMS. So on the right-hand side, we're going to have a 0. But then we want that -1 to show up sometimes and the +1 to show up sometimes. And so GAMS can do something very nice here that lets us do this in a compact way. So the thing that GAMS is quite proficient in is doing something like this. So let's say I have an expression that looks like A plus B and then $ and some kind of condition after that. So what this means is that B is only going to show up if this condition is true. And otherwise, B doesn't show up and we're just left with A. So let's see how that looks over here. So this means that the right-hand side here is going to be 0 pretty much all of the time, except this -1 is going to show up when the order of j, so what order of j is doing is it's returning the number of j in the set. So what does that mean? If we go back and look at the node set, the number associated with our 9 is going to be 1, the number associated with our 10 is going to be 2, and the number associated with our 17 is going to be 9. So this is just the order in which the nodes appear here in the set. And so here we're just saying this -1 is going to appear only for the first node. And this +1 is going to appear when the order of the node is equal to the very last thing in the set. So card j gives us the total cardinality, or the size of the set. So this +1 is only going to appear for this our 17, because that's the very last node. And if somehow I switched out the 15 and the 17 here, then the +1 is going to appear for the 15. But so I just want to point out another way of doing this. So another thing that we could write here, instead of ord j equals card j, is we could just write something like diag j our 17. So now this is just basically saying that this condition is only true when j is exactly equal to the node our 17. And so if we go back and look at this node set, even if we happen to somehow rearrange the node set so that our 17 is now no longer at the end, but somewhere in the middle, then this program will still work, because the +1 will appear only when our 17 is there. So let's continue running through this file. The next thing we do is we're going to take all of these equations and put them together in what we'll call a model. So our model is going to take into account the objective function and the network flow constraints. And down over here, we're going to solve that model. So we're going to solve the shortest path model we created using the linear programming solver and minimizing the objective function z. So that finds the shortest path. And the very last bit of this file basically opens up an output file that will cost minimum cost schedule.out. That's what we've decided to call it. So here we're going to print to it. And at the beginning, we're just going to print some kind of header. Like it's just going to say minimum cost schedule, some of these stars. And now we're going to have a loop. So we want to loop over all of the edges. But we're only going to take those edges whose y value is bigger than 0. So that's what this part of the file here says. So y.l means the level of the y variable. So here it's saying y.l, the level for the ijth variable, has to be bigger than 0, and only then can we do the inside of this loop. And the inside of this loop basically just prints out the start time of the person, the end time of the person. It goes and looks at that data table to figure out the person's name, and then the cost for which we're hiring them. And then at the very end here, it's going to print out the total cost. So let's try to run this file and see what happens. So when I run it now, it's going to give me an error. So, oh, well, it didn't give me an error this particular time, but it may give you an error. And if it does give you an error, the important thing to do is go and look at the very first error that comes out of the file here and try to solve that, because some of the later errors might be just due to the first error. So the reason I was expecting it to give me an error is because you have to tell GAMS where all of these CSV files are. So where in your directory structure on your computer they are. So right now I'm just giving it a name, but it doesn't know where it is. So to let it know where it is, you have to go to File, Project, and create a new project in the directory where all your CSV files are. So for me, it's in this GAMS directory. And so here I can create a project called New Project. And when you do that, it's just going to be empty. And then you can go and open the minimum cost schedule.gams. That's the file that we've been looking at. And so now when you run it, everything will be fine. Okay, so when we ran this, what it did was it created this minimum cost schedule.out file, this one right here. So let's just open it up with WordPad to see what it looks like. So this file printed out the header here, the minimum cost schedule, and then over here was that loop that was looping over all the edges, and it's only going to print out the edges with y values bigger than 0. So here, so those are the edges on the shortest path. So the first edge was from hour 9 to hour 13. It's going to get covered by Alice at a cost of 30. The next one is hour 13 to hour 16. It's going to be covered by Fred at a cost of 22. And then hour 16 to hour 17 is going to be covered by George at a cost of 9. And then the total cost is 61. So that's the basic idea for running this initial GAMS assignment. So for future assignments that I give you, you can use this example as something to work from. So you're going to be maybe messing around with the data file contents, the data file names, maybe the contents of this linear program over here, etc. Maybe you're even going to mess around with the way that these printouts work, but you can just use this file as a baseline. So that concludes lecture for today. Thanks a lot for listening.